My name is Eric Young, and I am presenting work I did with Katherine Kuchenbecker on ungrounded Vari-Dimensional Tactile Fingertip feedback for virtual object interaction. Previous studies have shown that cutaneous feedback alone can allow participants to reduce grasping forces, distinguish weights and directions, and follow virtual surfaces. Given a kinesthetic device, the addition of cutaneous feedback can improve curvature discrimination, reduce forces, and enhance perception of edges, textures, and friction. Clearly, cutaneous feedback can improve performance in many tasks, but how does tactile dimensionality affect user performance? We previously presented the design and implementation of a wearable 6-DoF fingertip haptic device called the Fingertip Puppeteer. In this work, we used the Fingertip Puppeteer, with a few design improvements, to evaluate how the dimensionality of fingertip cutaneous feedback affects performance in various interaction tasks. We designed a human subject study in which participants performed shape discrimination and mass discrimination in virtual reality. Users received fingertip feedback from one of 4 rendering methods. 3 methods consisted of 1, 3, and 6-DoF cutaneous feedback, and the 4th method included cutaneous and kinesthetic feedback from real objects. In the shape discrimination task, users explored and identified invisible smoothly curved surfaces similar to those defined in previous studies. The 1-DoF rendering presented the distance of the virtual surface, but the end effector maintained a fixed orientation relative to the finger. The 3-DoF rendering presented the distance and slope of the virtual surface. The 6-DoF rendering presented the distance and slope of the virtual surface, as well as friction in the form of 3-dimensional shear cues. In the mass discrimination task, users determined whether the mass of a sliding disc was less than or greater than the mass of a reference disc. For the 1, 3, and 6-DoF rendering methods, a penetration depth proportional to mass was required to move each disc, to simulate static friction. The 6-DoF rendering method also included haptic shear that was proportional to both the acceleration and the mass of the disc, to simulate the applied tangential force. Here we see a complete trial of the mass discrimination task with 6-DoF rendering. For each rendering method, participants completed the hidden surface task followed by the slider task. Within each task, users completed 2 training and 4 test trials. 20 users participated in the study. In the hidden surface shape discrimination task, all 4 rendering methods significantly outperformed chance. The real rendering method significantly outperformed all 3 tactile-only methods, suggesting kinesthetic and tactile feedback together are superior to tactile feedback alone for this shape discrimination task. We also observed better accuracies, times, and realism ratings for the 3-DoF and 6-DoF methods than for the 1-DoF method, matching previous findings that curvature perception is dominated by local surface orientation. However, differences between tactile rendering methods were not statistically significant, suggesting minimal benefit in providing higher dimensional tactile feedback in the absence of kinesthetic force feedback for this task. In the slider task, only the 6-DoF and real methods outperformed chance. We also collected and analyzed fingertip motions during the study. Overall, users implemented a wide variety of exploratory techniques. In the hidden surface task, some participants favored sweeping horizontal motions, whereas others preferred vertical poking motions. In the slider task, some users vigorously shook the slider side to side, whereas others made more precise, slow motions. Looking at finger speeds and accelerations for each participant, exploration technique does indeed seem to depend heavily on the individual. Interestingly, exploration techniques do not seem to be heavily influenced by rendering method. Although participants were only able to perform mass discrimination at rates above chance with tactile shear, the presence of this shear did not elicit significantly larger accelerations. Our naive users seemingly expected the tactile fingertip feedback to accommodate their exploratory tendencies, and as such, subjects did not adjust their motions to match the provided tactile sensations. For additional information and extended footage, please see our paper and supplemental material. Thank you.